All right. Today, the gradient vector and the directional derivative are what we're going to be talking about. Derivative. I'll just shut up and spell, I guess. Yeah, that's what we're going to be talking about. So here's the game. You've seen it before. A topo map. What? No. Like, what's the fastest way down this mountain and so forth. And where's the steepest place on this mountain? Well, it's clearly the steepest place right here. Okay, now, not real steep initially, right? And then all of a sudden, drops off the face of the earth, right? Because if this was, say, like 2,000 feet of elevation, and this was, better not count by 500s, I'll run out of 500s, I think. So this is 1,800, and then 1,600, and then 1,400, and then 1,200. Okay, one can see that, boy, it took a long time to get from hither to yon. Okay, yeah, that's a lot of moving. And then all of a sudden you go 2 steps and you drop 200 feet, and you another 200. Then wow, that's fast. That's right. So interestingly enough, if a person were standing, let's say here, for instance, hey, what's the fastest way down the hill? Well, from here, the fastest way would be to head this direction, right? It would be like, let's get to the next level. It would actually be like this. To get to the next level as quick as possible. Okay, it's the shortest distance. That's the steepest place. As soon as I get here, well, I'm going to turn and kind of head this direction now because I want to cross this guy the fastest I can. Then, of course, it's going to be more like this. And you're always going to find the path down the hill that is the fastest, or up the hill that's the fastest when you're talking about the gradient vector. So it is the direction that you go. Now, this is important. 2D, right? That is in the XY plane. Now, by definition, is to get the greatest positive change in Z. In other words, the greatest elevation change. So in other words, it's going uphill. Okay? Now, that's pretty straightforward. But meaning this is a 2D vector. Now, the way we write that is this. It's this upside down delta sign. It's the gradient of f. So our function was f of x. Is f of x and y is yada, yada, yada. So this is going to be thus. And it's like you're going to have it as an x and a y value. So it's going to be important. Where am I? And it's going to be a 2D vector. So in other words, it might come out something like this, 2, 1. Meaning that if you were at, let's say, the point 3, -1 on the graph, 1, 2, 3, -1, boom. You should head in the direction of 1, 2, up 1. So you should head in this direction from here. You should head in that direction. Yeah, in other words, from where you're at, you should head off that direction, which would be kind of like a northeasterly direction if you were looking at it from a compass standpoint. That's the direction you should go to get uphill the fastest. Again, on our surface, whatever our surface happened to be. Perhaps our surface was, come on, give it to me, you hippie. Calc plot 3D. There it is. Give it to me. Come on now. I have to use this stupid thing because my Google Chrome keeps crashing on this thing. Anyway, so let's say you were here. Let's put in a point. Let's just for a good time. I don't know. I'm just going to make up a point, and I hope it's on the graph, and we'll call it good. Nope, crap. I think it's just +1, dummy. Oh, that's pretty close. Okay, so if you were at that point that's on the graph right there, and I don't even know if it's actually, it is. We're going to pretend it's on the graph, okay? We're going to pretend that it's actually on the graph. But where would you go? Well, you'd clearly head towards this point up here, right? Now, where would that be? Well, in the XY plane, it looks like we've got positives and positives here. So in other words, you would head, for instance, toward the origin. So in other words, you would go, like, say, -1 in the x direction and -1 in the y direction. It would head, as you headed that direction, maybe I'd call that a southeasterly direction, you would head up the hill the fastest. Now, by the way, as soon as you move a little bit, what happens? Well, then it's going to change. In other words, your path up here on this topo map, as you started to move, you're like, well, wait, Mr. Grimm, you kind of followed a weird kind of a curvy path some part of the time. I did. I did. Because as I move, the direction of downhill the fastest changes. And if you don't believe that, go look at a topo map. We had one of these up the other day. St. Helens, Oregon. I'll do out here because I live out here, and it's cool. So don't go to our website. Just St. Helens, Oregon. Oregon. Yes, indeed. So click on this feller. Yeah, oh, I forgot. I got to go to Giggles first. Oh, that's so annoying. I hate you, Bing. I don't know if I hate you, but I don't like you sometimes. St. Helens. There you go. Cool. Whatever. Click on the map. I probably could do it in Bing too. I don't care. I'm not going to learn. I'm too old. I don't care. Give me the terrain map, yo. There you go. Boom. Yeah, there you go. So as you zoom in on these guys, of course, not the town, for God's sakes. As you zoom in on these guys, you'll notice that, hey, why does the creek go around the corner? All right? Why do things flow the way they flow? Well, they flow the way they flow because as the creek starts to flow toward the northwest or something, let's say, all of a sudden now the direction is downhill the fastest moves over to the east or something. So then you'll see it bend over to the east. It's the exact same thing. In fact, when you look at these draws, for instance, let's zoom in on one of these draws, where the creek, oh, not that close, dummy. As you can see that creek that follows down through that line through there, as they bend around, okay, you can see it literally following the fastest way across those lines. And it's always going to cross the terrain maps, which are ISO, they're ISO elevation changes. They're the same elevation. They will follow those and always in an orthogonal manner. Okay, and that's kind of the game that we'll always see. Okay, and so that directional or that gradient vector will always do that. But again, that vector, you think, oh, it's a straight line. It's a straight line direction at a point. That's what that means. It's a straight line direction at that point. Okay, but as soon as you take a step or two, why, that's all bets are off. Okay, all bets are off. So you're like, well, how do I find this gradient vector? Oh, see, that's easy money. Because as I mentioned previously, it is literally the easiest thing on the planet. It is simply f sub x, comma, f sub y. You mean the partials? That's right. If you prefer, you can write them as dz dx and dz dy. That's right. That's right, exactly. That's right, exactly. So, pretty cool. And in fact, you're like, wait, Jay, you mentioned something before, I feel like, about, you know, when we talked about that vector of the equation of a plane, and you talked about it from a vector standpoint, we saw something like this. We did, and we included a -1 in that guy for reasons because that's how it fit. But it's the same basic principle. And it's very straightforward. It's so easy to do. Let's do one, shall we? So if you add some f of x and y, 3xy squared. I really feel like I'm beating that one to death. Plus the ln of xy, sure, plus 6 sine x squared. Sure, I guess. Why not? So let's do it here. So the partials would be the following: 3y squared, 1 over xy times y, right? Because the derivative of the inside would be y with respect to x. Y is a constant. So y is going to end up on top. Oh, the y's cancel off. You're going to end up with this. That's nice. And then plus, this is going to be chain rule. So you're going to have to do 6 cosine of x squared times 2x. So it's going to be 12x cosine x squared. Nice. Ditto with the y's, very straightforward. It's going to be 6xy plus 1 over, well, it's going to be x over xy, so it's going to be that. And then, of course, that goes away, so that's nice. Wait, so you're telling me that my gradient is simply this guy? Correctamundo. You are correct. Well done. Well done. Clearly, this guy has an issue at 0. Okay, why does it have an issue at 0? And it has an issue negatives because obviously, what is the domain of the function? X and y. X and y both need to be bigger than 0. True. Could they both be negative? They could. This thing would exist in or x and y both less than 0. Now, again, why is that? Because if you take x times y, what do you end up with? You end up with a positive if they're both negative, and that would work as well. But it can't be 0. Okay, so we're going to see this when we graph it in a few minutes. We're going to see stuff happening in the first quadrant and in the third quadrant. So that's going to be true. And of course, nothing happens at 0 because the function doesn't exist at 0. So that'd be an issue, of course. So when we look at this, we're like, well, let's take a point. Let's see what happens at 1, 1, because I'm lazy. Okay, sure. Well, if you plug 1, 1 in, I'll do the hard part. 6 plus 1 is 7. That's hot. Okay. Now, in this point here, you're going to have, well, it's going to be 3 plus 1 is 4. 12 times, I don't know what that is. I'm going to have to get a calculator out. So 4 plus 12 times the cosine of 1. 10.48. Okay, meaning that if you're looking down on the xy plane, and I'm just going to stick I'm going to stick myself at 1, 1. This is what I said we were at, 1, 1. We're going to want to head off in a direction of going out here about 10 and up about 7. We're going to head off that direction. From 1, 1, we should head in this direction. Okay, that's what we're talking about. Okay, and so that's pretty straightforward. If I headed that direction, that is the fastest way up the hill. You're like, well, Jay, what if I went negative 10.48, negative 7? Then, friend, what you have just found is the negative gradient. And the negative gradient is the fastest way down. Nice. That's hot. Okay. And well, what would happen, Jay, if I went perpendicular to the gradient? It's a good question. If you went in a fashion that was perpendicular to the gradient, you wouldn't go up or down. It'd be like standing on a hillside. Like, I'm going to draw Mount Hood as if it was a cone. Are you with me? What if I was here and I headed north? What would happen? Well, initially, would you be changing heights at all? No, because you'd be moving tangentially. The fastest way up the hill would be here. The fastest way down the hill would be here. You'd be moving orthogonal to that, either direction, by the way. Orthogonal to that, either direction, or perpendicular, because it's really just two-dimensional. And guess what would be happening? Nothing. Now, as soon as you took a step, you'd have to change your direction to start walking this way. And if all you wanted to do was to walk around the hillside, you would just keep doing this, walking on a tangential to it all the way around. But of course, as soon as you take a step, you have to change your direction slightly because, again, you're going around a circle. That's it. That's it. And so it's pretty straightforward. Again, this is the negative gradient, and this is the positive gradient. Right, there you go. It's that easy, friends. Now let's look at this on a graph just for a good time on the old Calc Plot 3D. And let's get rid of that guy. I don't want him. You go away. No one wants you here. You're not wanted. I can't remember what my function was, although I feel like it's the same one every day. 3xy squared. Where's my keyboard? Come on, go away. 3x times y squared plus the natural log of x times y plus 6 sine of x squared. Oh, shut up. No one likes you. 6 sine of x squared. Whoa, look at that. Like, I'm shocked. Like, I'm not shocked. Because what I see here, well, what do I see? Well, what I see here is I see exactly what I expected to see. I expected to see stuff in the first quadrant and the third quadrant. That's nice. Now, take a peek at this for a minute. Let's put a little contour plot on this guy here. Let's see what happens. I don't know. What's that going to do for me? I guess that'll do it. Cool. Boom. There it is. Nice. Nice. Now, I'm actually going to go a little higher just for a good time. You can put more in. I don't know. I don't know that I've ever maxed it out. Contour plot lines wise. I don't know if I've ever done that. Normally, I just do whatever I do. It's fine. Now, look, where were we at? Okay, we were at 1, 1. Okay? And so what you can do is come on to this guy right here and put in -1. Oh, wait, no, right there. No, we were at 1, 1. Dummy. Oh, never mind. Don't change that. Don't change that. Don't change that. Forgot to tell you. Don't change that. Don't change that, dummy. No, just ignore what I said there. That's fine. Now, what I want to do is this. Well, you can do it a couple different ways. So let me back off here. Let me go ahead and add a point in. Oh, that was actually right. I'm actually right. Yeah, this is. They've changed it a little bit on me. So what you can do is drag this over to 1. I think you can actually type it in too. And there's your point on the graph. And you're like, well, yeah, okay, well, so what? So well, look what direction it needs to be headed. Okay, if you head it out, and I need to add a few more points here. So I'm going to click back out of this guy and click into here, I think. Yes. No, you go away. No. Where did my contour plot go? There it goes. All right, so what I'm going to do is I'm going to add some more because I want it to go higher yet, and I really don't care if I start at -2. I'm going to start at 0. I'm going to count by 2s maybe. There you go. Whatever. Don't really care. It's going to take me up quite a ways. It's not. It makes sense because it's going to be pretty high direction. Like, in other words, pretty high stuff out there. For whatever reason, it's stopping at 8. Why is it stopping at 8 height-wise? Let's see here. Do we need to change something in here? Yeah, maybe. No, I don't think so. All right. Anyway, the point is what is the point, Jay, exactly? Come on, bud. All right, so anyway, so anyway, headed out towards, in the direction of, let's do it this way maybe. Let's back off. Anyway, we're heading out in the direction of this. Let's see here. We are at, so we're heading off this direction of 10.48, 7. In other words, we saw these guys coming through like that. We head out this direction, we're going to be climbing the hill the fastest. Okay, I'm going to do a different one here in a second and show you that maybe there's a better one that you can kind of maybe wrap your heads around. So I'm going to do this one here. Okay, this is a really easy one. This is a cone. It's upside down. Well, is it a cone or is it this? Okay, I won't tell you what it is. Let's just see what it is. Well, we won't worry about what it is for right now. Let's do this. So if you take the gradient, and again, typically written that way, it's going to be thus. Nice. And so if you are at 1, 1, for instance, if you were at 1, 1, the gradient of f at 1, 1 is going to be -2, -2. Meaning that here you are, you should be headed this direction, okay, back toward the origin. Would that be true at, say, I don't know, a half, comma 1? And the answer is no, of course not. It would be -1, -2, which means that if I was at a half, it should be here, 1, I'd be headed over 1 and down 2. I'd be headed again towards the origin. You can see that. Now, why is that? Well, in this case, what's that telling me? That's telling me that this one, when I graph it, that means the origin was my high point. It was my maximum, something we'll talk more about later on. And this thing's kind of getting on my nerves. You go away. No one wants you here. Leave. No, I don't want that. Why is that stupid thing here? I don't know what's wrong with it. All right, here we go. So, I don't need 2 of you. Oh, nice. That's hot. Okay. Now, again, the guy puts in 1, 1. You're going to get 2, right? You need a point 1, 1, comma 2. So I come in here and I can put in a point. You can add a point wherever the point went. I swear I saw it a minute ago. There it is. And let's do this as 1. Again, I put in 1, 1 for x and y, and I got out 2 for my z value. And I'm going to make it stand out from the crowd because that's what I do. That's nice and garish. Hit enter. And somewhere on this thing, there's my point. Okay? Now, keep that in mind. If I scroll this around, where am I going to have to head? Well, I'm going to head toward up the hill. But if you view it from above, which it's easier said than done this direction sometimes. Okay, but look, here I am at 1, 1. It doesn't really look like it. It's optical illusion, man. I got to head toward the origin because the origin, 0, 0, 4, that's what the highest point is. In other words, I'm going to go 0 on the x-axis. And by the way, my x's and y's are shifted there, so pay attention to that. I'm going to go, it's really hard to switch that around. Now, you can actually view it a little differently if you're capable. Right here, plot view settings. You can actually view it from above the XY plane. So looking down the XY plane, there we go. What do I need to do? I need to head towards the origin, which means I got to go -1 in the X direction, -1 in the Y direction. That's the direction that my gradient will point, okay? Now, you can also, when you're doing this, if you click back on this guy here, put your contour plot back on. I don't need to go this high anymore. So 0 is fine. Let's make it count by 0.1s or something, I guess, because why not? And where's that going to put us? It's going to put us at 2.9. It's not high enough. Let's go 0.3 or something. And what is that going to do for us? It should work. Yeah, because our maximum was 4 height-wise there. Yeah, sweet. And so you can see us here at the yellow. And which direction? Man, I got to go this direction. Now, because this is a nice, perfectly circular situation, as we're heading towards the origin, right, I'm going to continue going that way the whole time. But that won't always be true. For instance, suppose you had this guy. Just shake it up a little bit here. Let's get rid of this point. Let's shake this up. Let's put a 2 in here. What? Okay, now I got to change my view settings. Sorry, I got to get rid of my view settings here. Reset 3D view. There you go. Cool. And you're like, oh, well, this is weird. It's it's a different shape now. You know what I mean? It's kind of an oblong shape now. That's right. That's right. So let's check it out. Okay. And so you're like, oh, all right, let's do this. Cool. All right. I don't want you to change my settings, for God's sake. 4 minus x squared minus 2y squared. Nice. So this is your f of x and y, whatever. All right, cool. So what would the gradient be? Well, the gradient would be negative 2x, negative 4y. Nice. And so if you were at the point, now where would the point be now? Well, the point would be, I could say 1, 1, because that's clearly there, right? I could say, which way do I go at 1, 1? That's still doable, right? Notice that I'm not the same elevation I was before, because if you put 1, 1 in, you're going to get 1 minus 1, you're going to get 1. You're going to get 1, 1, 1 instead of 1, 1, 2, like we did last time, which is not shocking. But I'm talking about here. This is, if you will, a latitude-longitude situation kind of a thing, right? In other words, here I am at the latitude, longitude of this and such, okay? Now, which direction do I go from here to get uphill the fastest? Well, that's what we're talking about from a gradient standpoint, okay? And it'll say, like, go on this, go off at a, north 30 degrees east, or, or maybe it'll do a 222-degree compass heading or whatever. That's what it'll say. Does your GPS tell you what your elevation is now? Some of them do, some of them don't. Most of them do now. My old one didn't, but yeah. And so you'd be going along going, oh, yeah, it doesn't tell me. It just tells me where I'm at latitude, longitude-wise. That's the idea of when I tell you I'm at 1, 1. I'm telling you that's my latitude, longitude situation, okay? The Z would be, in essence, my elevation. And that's fine. I'm not interested in what my elevation is. I'm interested in which direction do I go to increase the elevation at the fastest rate. That is what the gradient is telling me. So again, if you plug 1, 1 into here, you're going to get what? You're going to get negative 2, negative 4. And what does that tell me? It says here I am at 1, 1, and I need to go negative 2, negative 4. I need to head this direction to get uphill the fastest, okay? But it will not stay that way, okay? Because think about this for a minute. Suppose you went this direction just a teeny skosh of a distance. If I started at 1, 1, and let's say that I moved in this direction, but just a little bit. In other words, picture those, if you will, as speeds. Let's say it's negative 2 meters per second, and it's negative 4 meters per second. Okay, just go with me on that for a second. So if I went that way, just a skosh, like for like 1 second, or like not 1 second, like 0.1 second or something. Let's say I went negative 0.2 in the x direction and negative 0.4 in the z direction. Did I still go the same direction? I did. I scaled it down. In other words, just a little ways. Now, where am I at now? Well, now I'm at 0.8 because I was at 1 and now I'm at 0.2 in the x direction, right? And I went negative 0.4, so that'd be 0.6, I guess, yes? Nice. So then my question would simply be this. Is this the same gradient now? And the answer is I don't think so, but we'll find out. And that would be, again, you plug it in there, 2 times 0.8, negative 1.6, and then 0.6, negative 2.4. Okay? Well, notice this is a 2-to-1 ratio there, right? Is this 2-to-1 anymore? No. So what does that tell me? It's going to tell me then that I'm going to end up going more, right? It's going to be changed up the direction that I travel. And by the way, notice that this direction here, this 2-to-1 slope, you're like, Jay, you're going to miss the origin. Wasn't the origin where it was, that was the high point, right? It was 0, 0, 4. Yeah, you're right. So as I come this direction a little ways, guess what's going to happen? It's going to flatten out. And where am I going to head? I'm going to head toward the origin. And eventually I'm going to get to that origin point. And so as we start to talk about these things, just keep that in mind. As you start to move, right, things change. And if you come back over here, let's go look at that contour plot there. If I'm here at 1, 1, no fart. Oh, that's just stupid. My contour plot went away. That's very annoying. Anyways, if I head, again, over to down 4, I'm going to miss the origin. But I know that's the highest. Okay? As I come in this direction, things are going to change. Okay? Now, you can actually view the... I'm going to figure out where to find it on this stupid thing. They've moved everything around so many times. I think you can do it this way, actually. No. Where is it hiding? Oh! Oh, by the way, up here on top, you come back up here, put this at 1, 1, dummy. Put that at 1, 1. If you put that exactly at 1, 1, at the top of the page there, it'll tell you. Okay, that should make me dizzy. Stop it. Oh, there it did it, what I wanted it to do, but I didn't really know where it was. There it is. Anyway, if you do that, it'll tell you at the top of the page, f of 1 and 1 is 1. You see that? That's the y value, the z value of it. Now, if you click on this point here, you click out here on this point anywhere, and for whatever reason, I'm not sure why it keeps popping up. Anyway, if you click on this point, it should say, show the gradient at the initial point. And it'll tell you what the gradient is. Okay? Notice that they use this guy here. Now, again, notice that that gradient vector is a 2D vector. I cannot stress that enough. Cannot stress it enough. Now, watch the gradient move as I move. So there it is at 1, 1, roughly, right? Here, as I come this direction, look what happens to my gradient. It changes, and it ends up pointing towards the origin. You see that? And so that will always be true. Now, I do not want you to use the computer to find the gradient. What I want you to see is that as we move and change things, what I want you to visualize by using this situation is, look, if you walk this direction, you'll never get to the top of the hill. If you keep walking this way, you'll come up over the side hump and down the other side, and you're like, where did I go? I never saw the top. But as you start moving this direction, notice that the gradient changes. So I start coming and walking always toward that gradient, and lo and behold, where do I get to? The top, the maximum. Okay? That is a big deal. It is a big deal. Okay? Not hard, but it's a big concept. That's something I want you to fully understand. Now, the second thing that I want to talk about today is the concept of, well, Jay, it's too steep to walk straight up the hill. Well, yeah, duh. Well, what if I instead take a not as steep route? Well, then you get to the top eventually, but not right away. And I want to do the 2y one. And again, I'm going to stick with an easier one just for the sake of argument. We already know that the gradient here is, there's an x, stupid. Okay, there it is. We already know that's true. That's not new or exciting or anything. But what I want to tell you is this. If I'm at the point 1, 1, and I walk in the direction of -2, -4, I go uphill fastest. That's true. We know that. That's literally the definition of a gradient. But what if I walk at a direction of 1, 1 instead? Will I still be going uphill? And the answer is, in this case, well, yeah, I will. Jay, how do you know that? Okay, well, first of all, check this out. If you were to find, there are two vectors that are orthogonal to this guy in the xy plane. One of them is this guy. Is it? Yes. Yes, yes. Because remember, they're negative reciprocals of one another. So check it out. -2 times this is -8. In other words, they'll have a dot product that's equal to 0. That's -8. That's +8. They get 0. They'd be orthogonal to one another. And of course, so is this one. But that one's negative and that one's positive. Okay? So if you're walking on either of those, oh, you go away. No one likes you. So if I were to walk at -4, 2 or 4, -2, no elevation change. So let's lay this off on the old grid. Here's 1, 1. That's my starting point. So we're saying we should walk this way to get uphill the fastest. We should walk this way to get downhill the fastest. This direction, there is no change. This direction, there is no change. No change. No change. Max increase. Max decrease. Therefore, if I were to walk towards the origin, would I still be going uphill? Yeah. But not as fast uphill. Are you with me? Not as fast. All right. Now, again, I like to think about this as for hiking purposes, and I don't mean you people that like, oh, I'm on a 72-mile hike today. No, it's just common sense. Like, hey, that clearly, if I walked up this face of this hillside here, that would be the fastest way up the hill. Faux show. 100%. I agree with you. 100% I agree with you. However, you have to be careful here, because what happens when you do that? Okay, you can't walk up that cow's face. It's steep. You can't do that. So what do? Well, you head off a little toward Canoyers there. You're still going to get up the hill, but you can actually stay on your feet while doing so. Okay. When you build a road, all right, you can't drive straight up that hillside. So you build in a bunch of switchbacks so that you can. In essence, what you're doing is you're still climbing, but you're reducing the rate of increase. Right? That's what you're saying. So what we're going to talk about now is what's called the directional derivative. What do you mean, Jay? Well, I mean this. You give me a derivative. You give me a direction, and I will tell you, what does this mean? The rate of change. So for a given direction, wait a minute, doesn't that entail a unit vector? That's right. Because remember, we talked about unit vectors. They are 1 unit long. So the only thing they talk about really is which direction. That's all we talk about. Okay, so which direction are we going in? Okay, and they're a unit vector. Okay, and so what we're going to do, given a given direction, the directional derivative talks about the rate of change in that direction. Direction. Good Lord, learn how to spell, you loser. Okay, so we're going to come up with a unit vector that is cleverly called u. And it will be of a point AB. And it will not be a point, you jackass. It'll be a vector, so you're going to use dots like so. Okay, and what we're going to do is we're going to take, and you're going to be shocked by this. I know you are. I know you are. Because what is this? This is a delta x, and this is a delta y. Check this out. We're going to take the gradient vector. What? Dot the u vector. What? And we are going to get out a scalar. Now, what will that scalar mean? This is the rate of change of z in the direction of u. That's it. That's it. But why does it work that way? See, I'm glad you asked. Because what is the gradient? Well, the gradient is, by definition, dz, or a change in z, dx. A change in z over a change in x. And a change in z over a change in y. So when you take the dot product, you end up with dz dx times delta x plus dz dy times a delta y. For a grand total of basically a big delta z. That's it. That's it. A delta z, Jay, but over what? I'm glad you asked. Over 1 unit. What do you mean over 1 unit? Well, what was the directional derivative? It was 1 unit long in the xy plane. In other words, looking down on the xy plane, if we're here and we travel 1 unit this direction, 1 unit. Well, I'm tired of doing that one. Let's start here, and let's travel 1 unit this direction. 1 unit. The question is, it's 1 unit here. Now viewed from the side, down here is the xy plane. It's 1 unit here. There is my delta z right there. So the slope is this guy over this guy. That is literally the definition of the directional derivative. It's that easy. It's that easy. Okay? Let's make it happen. Okay? So let's come back to this guy here. So the one we just did a second ago. Well, I wrote it down, but I think I lost it now. So I think we had this. We had f of x and y. And it was 4 minus x squared minus 2y squared. Again, I don't want to get bogged down and taking a zillion derivatives. You will do that on your assignment. Good for you. But really, the concept is the part here that's exciting. Okay, if I'm at 1, 1, I know that the gradient for 1, 1 should be -2, -4. But I can't walk that way. It's too steep. So what do I do instead? Well, instead, what I do is I go, all right, let's do this. First of all, I want to head in the direction of, let's head in the direction of -1, -1. Oops, I want to head this direction. Now you're like, Jay, that's not truly a direction. No, I agree with you. Because how long is this guy? Okay, well, let's look at it. So any vector, if you go -1, -1, well, the length of it is the square root of 2, am I right? So this guy here is not truly our unit vector. Our unit vector is this fella. Does that make sense? You need a unit vector, but in that same direction. So I could say something like, head in the direction of 2, 7. You're like, Jay, that's not a unit vector. I know. You need to make it a unit vector. Okay? And so it's not very difficult. And then what a fella does is simply goes -2 times -1 over root 2 plus -4 times -1 over, oh, I'm sorry, not -1, you idiot, times 1, oh yeah, -1 over root 2. And lo and behold, what do you get here? You get 2 over root 2 plus 4 over root 2, which is 6 over square root of 2, which is, I don't know, I can't do math. About 4.24. So for every 1 unit in the xy plane you move, you will be going up 4.24 units in the z direction, in elevation. And I'm like, that's great. Do another one. Okay, cool. So what would if I'm starting at 1, 1 and I move in the direction of 3, 1, okay, what will the rate of change be? That's a great question. Let's do that, shall we? So 3, 1 is not a vector. It's a vector, but it's not a unit vector. So let's draw that picture up. 3, 1, whatever, square root of 10. Are you with me? That's the magnitude of that guy. So let's call our u 3 over root 10, 1 over root 10. Nice. Oops. It's a vector, you ding-dong. Now let's go ahead and multiply it out. All right, let's do it. So if I were to do that, then I would have, remember that my gradient was -2, -4, I believe. I almost freaked myself out because I said this problem have to do a certain thing, and then I thought, oh no, what's wrong? But then I'm like, yeah, it's absolutely right, you moron. So -6 over root 10. And then, of course, plus, I guess that's multiplying it out. And then, of course, -4 over root 10, which is -10 over root 10, which is just negative the square root of 10. You're like, wait, what does that mean? It means that you're going to come down about 3.16 meters for every, let's say if it's in meters, for every 1 meter you travel in the xy plane. What's negative? Yeah, I hope so. I hope so. Again, come back to our picture that we had up here on the previous page, I think it was. Okay, if I'm here and I head over at 1, 2, 3, up 1, well, this was no change. Anything on this side is going to be going negative. How about that? So I'm coming downhill going this way. Am I going down as fast as I could have been? No, not at all. Not at all. Now, we have said it before, and I'm going to say it again. which is the fastest way down the hill, is always to move opposite the gradient. So if our gradient was -2, -4, what if I were to move in the direction of 2, 4? What would happen? Well, let's find out. I'm glad you asked. Remember, this is not the u vector, but this thing has a magnitude of square root of 20. So if you were to do this, you would again take that and multiply it out. You'd get -4 over root 20, and then you would get 16 over root 20, and you'd get -20 over root 20, which is just the square root of 20. And you're like, negative. And you're like, well, what does that got to do with anything? Well, check it out. What is the magnitude of this guy? The magnitude of the gradient vector is the greatest rate of change that you can ever get. Greatest. Because that is the fastest way going up the hill. Fastest meaning what? The greatest rate of change. So the magnitude of the gradient is the greatest rate of change you can ever see. Period. So had you moved in the direction of -2, -4, which by the way would have been here and here, then I would have gotten positive square root of 20. If I go directly opposite that, completely opposite direction, I will get negative square root of 20. And everywhere in between will be something different. You recall a minute ago, square root of 20 is 4.5-ish. Call it 4.5-ish. A minute ago, we got the square root of 10. That's 3.16, Jay. Oh, that's right. And what if I'm awfully close to going perpendicular to it? Then I'm going to get awfully close to 0 rate of change. That's it. There's nothing to it. It's almost fun, to be honest with you. Almost fun. It's kind of fun. It's kind of sort of a good time. I don't know. Jay, is it possible, Jay, that you could have more than 2 directions? In other words, could W have a gradient vector if it's x, y, and z? Sure can. And it's exactly what you thought it would be. If W is a function of x, y, and z, then your gradient vector, because this is 4 dimensions, your gradient will be dz, dz, you jackwagon, dw, dx, dw, dy, dw, dz. And it'd be 3-dimensional. Again, think statistics. Don't get hung up on graphing things. Okay, we're not going to do a ton of that, so don't get all weirded out by it. Here's an example that your book likes to use, something like this guy. So, we're going to fool you. We're going to go G of R and S. All right. So G of R and S, okay, and is equal to the arc tangent, because why not, of R and S, or times S rather. And then our V, so we're talking about at the point 1, 2, and we're going to head in the direction of this guy. Why did they do that? I don't know, because they're weird, man. It's just one thing at a time, friend. One thing at a time. Now, Jay, we need to find the partial derivatives of arc tangent. Yes, we do. So the derivative of the arc tan of, and I'm just going to use x times y, and I don't really care, and comma x, like so. Sure, there you go. So it's going to be, so if I used x for my a, then it's going to be b over a b. No, I'm sorry, we're going to use an rs here. So it's going to be s over r squared, s squared plus 1. And this is the, yeah, well, I'm just going to do them like this. I don't really care. And I'll do it the other way around. I think it's pretty clear that it should be the same, but put an x on the top, sure. Nice. Cool. So what happens at 1, 2? Well, I don't know. Okay, at 1, 2. So it's going to be 2 over, and then it's going to be 4 plus 1 is 5. I guess the other one would have to be 1/5. Beautiful. Okay, so I'm going to voice over this next part here. I got done, and I realized I had made kind of a weird statement. It kind of freaked myself out. And then I'm like, what? And then I realized I made a mistake. And I don't really go back and fix it. You see me there. What I did on the calculator was I tried to like show, hey, the magnitude is 0.2. The problem is the magnitude isn't 0.2, you dim bulb. It's the square root of 0.2, which would be 0.457 or thereabouts. Okay. And that kind of weirded me out for a second, because in a second, when we get done doing the gradient vector here, which we're going to do, we're heading off in the direction of 5, 10. Or so we're heading out in the direction of, we're at 1, 2, and we're going to head out in the direction of 2, 5. That would be this gradient. In other words, we're going to go twice as far to the right as we are up. And then here I'm drawing, if you go back the other way, it's not increasing at all, it's decreasing. And then of course here along these lines here, these the ones that go up and to the left and down to the right, those guys are obviously in a situation where you're going to be changing it at all. Then that arrow I just drew is the direction of 5, 10. But notice that's not a direction. It's not a unit vector. So the magnitude there is the square root of 125. So there's that. Nice. And so then let's just simply do the directional derivative here, which is the dot product. So when I get this in a few minutes, I'm going to get something like, I don't remember what it is, 0.35 or something, which in my mind was weird compared to the 0.2, but it really wasn't, because I didn't square root the 0.2. And had I done that, I would have gotten the correct answer. So once again, as I said before, the magnitude of your gradient vector is the maximum rate of change that you can see at that point. Okay? And go in that direction. That's the most that you'll ever see. So here I get 0.357. It kind of weirded me out for a second, because like, wait, what did I do wrong? Again, if you square root to 0.2, you would have had the 0.457 that we should have had anywho. So just be aware of that. And I think I'm talking to myself here in the video, and I'm getting a little irritated with myself. And then I'm like, wait, what's going on here? All right. And I don't know what I did. See, I accidentally took the square root of the wrong thing there, which if I had taken the square root of 0.2 like I planned to do, I would have caught myself, but I didn't. Anyway, so whatever. Okay. Darn it. So apparently I deleted all my voiceover from this part. Yay. So here's another example problem. This one's a little different because it gives us literally a direction. It says, let's go at a direction of pi over 3. You're like, wait, what is that? I'll show you. It's all good. So here we go. Let's take the directional. Let's get going, Jay. Let's go. What's your problem, Pud? Let's go. Obviously, I could change this over, and we could look at it from a standpoint of, when I say pi over 3, we could also use polar form. Could. Kind of am, kind of not. Really what I'm going to do is convert back to rectangular form here in just a second. So here I go. I'm going to find the gradient vector. This would have been a lot more satisfactory had I split it differently. But oh well, it's okay. It'll be fine. It'll be a good time. So there is your, for x, nice, there you go. There's your x coordinate, or the x portion of the gradient. And then let's take it with respect to y. And then you're going to have the x squared cosine of xy. Nice, boom. Nice. And if you plug the 2 and the 0 in, so x equals 2, and remember that second 5, 8, 8, y equals 0, you're going to get 0. So 0 in the x direction, meaning we're going to go vertical, either up or down. And then plug the 0 and 2 into the other one. Of course, the cosine of 0 is 1 times the 2 squared out front is going to be 4, which I didn't see that, and I see it now plain as day, but I was too busy punching my calculator. There it is. So we're going to go straight vertical here. And notice that the magnitude of this guy is 4. So if I go 1 unit in that direction, I will go up 4. If I go down, that's going to be going down. And then, of course, on the x-axis, there's 0 change. Pi over 3 is a 60-degree angle off of the horizontal. And so you're like, well, how am I going to get a x's and y's for a vector? Well, I'm going to do the cosine of pi over 3 and the sine of pi over 3 as if we were in a unit circle, because literally a unit circle, the radius of a unit circle is a unit vector. Okay, so it's going to be cosine of pi over 3, comma, sine pi over 3. Cosine of pi over 3 is a half, but it won't matter because it's going to be times by 0. And then the sine of pi over 3 is the square root of 3 over 2. So 0 plus, and then it's going to be 4 square roots of 3 over 2, which is 2 square roots of 3, which is 3.4-ish. Okay. Notice that, again, 3.4 is less than 4. 4 is the most we would have gotten had we gone, in the vertical direction. Okay, so not terribly shocked by that. Okay. And then let's see, what do I do here? What do I do? I thought I did something else here. Oh, I did. Yes, I said, what if I went, well, that's right, what if I went, this is if I go vertical. You see, I get 4. Nice. If I go 1 unit in the vertical direction. But what if I go 1 unit horizontal? What would happen? If I went 1 unit horizontal, or 2 units horizontal, or anything horizontal is going to give me 0 for a directional derivative. And I can see that obviously from the mathematics, but also from the way I have it drawn up there. If I go horizontal, so I go 2, 0, let's say, or 1, 0, doesn't make any difference really. But 1, 0 will be a unit vector. So in this case, 0 times 1, 4 times 0 is 0. And again, if I stay on the horizontal axis there, nothing's going to change. Boom.